I'm opening now the next session with Zhikang Deng.
Yeah.
He's going to be our next speaker. He is a PhD researcher at ETH in Zurich, and he's going to talk about a very exciting topic of reinforcing glass or glass beams with an iron-based shape memory alloy. So I'm really curious about your presentation. The floor is yours.
Thank you. Thank you for your introduction. My name is Zhikang Deng. I'm a PhD student from ETH Zurich, Switzerland. I would like to give a presentation on the topic of structural performance of glass to shape memory alloy adhesive shear joints, considering the effect of temperature. I'll start with some backgrounds and the objectives of our research, followed by the materials involved in our investigation. Then we did some tests to investigate the performance of our design. Later, I'm going to show you some results and our future investigations. I'll start with the background. The background of our project is we would like to, as most of you know, glass are increasingly applied for structural elements like glass beams or fins as the first figures. So what we are doing is trying to improve the structural performance of the glass beam because glass is quite brittle. So if there's a crack, then perhaps it's gone. So we would like to increase the structural performance of this kind of glass beam. One typical method is to reinforce it with the tendons at the top and the bottom. We have tendons at the top and the bottom, and we use adhesive to bound the tendons and the glass beams. In this way, we can improve the structural performance of the glass beam. However, the peripherally used post-tension reinforcements like steel, stainless steel, they can improve the structural performance. However, they are also quite complex and expensive. If we want to pre-stress in the tendons, if we want to pre-stress the steel, normally we use special setup to do that. That's why we designed this kind of concept. We are trying to reinforce the glass beams with shape memory alloy. This iron-based shape memory alloy. We adhesive bound the shape memory alloy at the top and the bottom. So in this way, we can improve the structural performance. Shape memory alloy is kind of materials with the shape memory effect. This kind of material is specially designed mainly for civil engineering, because for civil engineering, we should consider the price also. So it was used for reinforcing concrete, steel, bridge, or normally for civil engineering. So we are trying to use it on glass with the adhesive bonding. So this kind of shape memory alloy, it will pre-strained first, then we will unloading it. After unloading, we will have some rigid deformation. So as we can see, it's longer than the initial state. And this pre-stressing shape memory alloy is done in the company. This shape memory alloy will deliver to our lab. We do adhesive bonding to the glass beam. So we can heat the shape memory alloy. After heating, because we have some rigid deformation for the shape memory alloy, after heating, the shape memory alloy will shrink back. This is called the shape memory effect. So after shrinking back, we will have a compression force for this glass beam. In this way, when the glass beams are subjected to bending load, we will have a compression force at the bottom. In this way, we can improve the structural performance. This compression force can are good for the bending performance of this glass beam. So we did some 4-point bending test of this of this kind of design. We have the red one is the adhesive color. So we have the shape member alloy at the top and the bottom. We bound them together with the adhesive. So we do 4-point bending, and we prove the feasibility of reinforcing beams with the adhesively bonded shape member alloy. And we can see the curve here. This is the load displacement curve for this 4-point bending test. Here is the peak here means the crack initiation. So the red one is with shape member alloy that is which is reinforced with the shape member alloy. Is this kind of concept. And without shape member alloy is the test without the adhesive bonded shape member alloy. We just put a shape member alloy at the top without any bonding. So we compared the results. We found that the load of crack initiation increased a lot. It's almost 2.5 times higher. And also we have a ductile failure mode. This means that after cracking, these kind of glass beams are still capable of carrying loads, which means that it's also safer. So we can see that this kind of design is stronger and safer. However, if we would like to use this kind of design for facade engineering, sometimes its exposure to sunlight and the temperature can be high. And we use the adhesive here, which is normally sensitive to temperature. This adhesive has a glass transition temperature of 67 degrees. And for civil engineering, the temperature can be as high as like 80 degrees. So we would like to know what will happen if the temperature increased. So our this investigation, we would like to access the feasibility of strengthening the glass elements with the adhesive bonded shape member alloy at elevated temperature. We want to know if the temperature elevated, if they are safe. And we want to know the structural behaviors of this kind of design, and we want to also know the limitations of this kind of design. So this is the materials we used for our investigation. We used the adhesive, which is a commercial available in the market. It's a 2-component epoxy. As we can see here that the elastic modular decreased a lot at 80 degrees, and also the tensile strength decreased a lot at higher temperature. So we were worrying what will happen if the temperature elevated. So that's why we do this investigation. And this shape member alloy is also a commercial product in the market. It was price-ranked by 2.5% in the factory of the company, and it was delivered to our lab. We do the test, and this is the near glass we used for our test. So because we would like to first investigate the bonding behaviors of the glass and the shape member alloy, so we designed this kind of specimen. We have the glass at the bottom, and we have this black one is the shape member alloy. We have the adhesive in between, so we can do a lap-shear test to see what is happening at a higher temperature. And we did a test at room temperature 50 degrees and 80 degrees, so one temperature before glass transition temperature and one temperature higher than glass transition temperature. And we use DIC and RVD to measure the slip behavior. And this is the setup we designed for this specific test. So the white one is the glass. The black one is the shape member alloy. We have adhesive in between. So we fix this part. We pour this shape member alloy, and this glass is supported by this frame, by this steel frame, so we can have a shear behaviors of these joints. And we put the whole setup in the laminar chamber like this, and we heat the laminar chamber to a specific temperature at room temperature 50 and 80 degrees, so we can do the test at a relatively stable temperature to see what is happening for this kind of shear joints. And this is the test setup configuration. This is the specimen. This specimen I mentioned on my previous slice, we have the this is the steel frame, this is the glass shapewear alloy, and we pour one end and fix another end, and we hang the whole setup in the climate chamber. We use the two DSC cameras to measure the strain field of this kind of test, and this the speak pattern we used for DSC to track the strain of this test, and we used the LVDT to measure the slip behavior of the shear joints. So for this one, the LVDT one, the base is supported on the glass, and this LVDT is supported on the shapewear alloy. So we can see what is the relative displacement between the shapewear alloy and the glass. And with this, what we do with the DIC, we define some nodes on the DIC, so we can know by these equations we can know what is happening for the test at room temperature 50 degree. And the DIC were used for this kind of for this two temperature, because for this two temperature we can keep the climate chamber open and heat the climate chamber, and we can have a stable temperature for the whole specimen. For 80 degree, because it's quite high, if we open the climate chamber, the temperature is not stable. So for the higher temperature at 80 degree, we use the LVDT to measure the slip behavior. And the test load is a displacement control at a relatively low speed in order to measure the crack initiation and propagation. And this is the failure mode. For this test, for this lap-shear test at 3 different temperatures, we observed different failure mode. For the test at room temperature, we can see there is a cohesive failure mode. Even the adhesive on the glass is quite thin, but there is still a thin layer of the adhesive. This means that this kind of failure is due to the failure of the adhesive itself. At higher temperature, we have the adhesive failure. This adhesive failure is means the interface failure between the adhesive and the glass. So at 50 and 80 degree, we have the failure due to the weak interface between adhesive and the glass. This will give us a hint if we want to improve the structure performance of this kind of design. What should we do? For room temperature, yeah, because the adhesive already the adhesive failure, that means that, yeah, if we want to improve their performance, we need to change the adhesive. For this one, it's due to the weak interface between the adhesives and the glass. So if we want to improve their performance, we need to increase their interface strength. We could perhaps do some interface modification or apply some primers to improve the structure performance. And this is the load displacement curve for the test at a different temperature. The black one is tested at room temperature, the blue one is 50 degree, the red one is 80 degree. We can see that if we see the load, we can know that for a test at 80 degree, the load decreased a little bit. Yeah, it's not as what we see for the adhesive. For the adhesive, if we read the data from the adhesive, for the data sheet of the adhesive, we know that the strength of the adhesive decreased a lot. However, in this kind of design, even the adhesive strength decreased a lot, but the adhesive is more ductile at a higher temperature. This is good for this kind of design. So we can see that the load carrying ability decreased, but it's there is okay because it's there here, 80%, and for this is the load slip behavior. From this curve, we know that here is the crack initiation, we have crack propagation. So we know that for test at higher temperature, at 80 degrees, we still have a ductile failure mode. Even the ductility is a little bit lower compared to room temperature and 50 degrees, but still is okay. This means that, from this curve, we know the ability and the limitations of our design. And this is our effective bound length for the test results. Effective bound length because it is a length at for the bounded joints, which is taking the shear force because we have relatively long bound length. This is 450 millimeter, and not when we apply the load, not over this 450 are activated. That means only part of these are activated, as we show in the. Sorry. As we show in the DRC, you see, this here is the shear force happening. This means that this part is important. So if we want to make our design safe, we need to make sure at least we have we should have at least a specific lengths that are carrying the loads. So this is an important factor for our application. That's why we need to define it. So in this curve, we use this is based on the DRC measurement. We know the effective bound length for room temperature is 130. So it means that if we want to make our design safe, we need to at least have a 130 millimeter bound length. So if the bound length is too short, then we will lower the strength of these joints. And for 50 degree, we have 200, and for 80 degree, because for 80 degree we cannot use DRC anymore, so we use the strain gauge to measure the. We applied 10 strain gauge along the bound length, and we see how many strain gauge are activated, and in this way we can define the approximate effective bound length. For 80 degree is 250 to 300 millimeter. And this is the main conclusion. The main failure mode is changed from room temperature to higher temperature. This will give us a hint how to improve the performance of our design. And the ductile failure mode can still be achieved. However, the ductility is lower. And the load carrying capacity is 18% lower at 80 degrees, but it's still okay. This will give us a hint of our limitation of our design. And the effective bound length is changed. So if we want to use this kind of design at high temperature, at 80 degrees, we need to give the design a longer effective bound length. So our future investigation will focus on long-term behavior and considering the humidity and the UV on the bounded joints and how to apply this kind of design in a real practical projects. Finally, I would show my thanks to our sponsors and thank you.